I'm thankful for the opportunity to share with you at this year's SPP conference some ideas on how we as a community of physicists and physics teachers and mentors can make physics, our subject that we love, less intimidating. I think it won't come as a surprise to most of us that that physics is an intimidating subject for many people, many Filipinos. So when I was to do research for this topic, I asked my Facebook friends to share some stories, their experiences of learning physics in school. And indeed, I got many comments that reflect that experience that physics is difficult and intimidating. So I'm going to share with you some of them here. These two comments are saying they spent so much time solving problems when physics applies in everyday life. Yun. And that they wish that this was brought down to that level more. So there's this recognition that there's a disconnect between how physics is taught in school and what we now know physics is. You know that physics is actually explains everything around us. So nasasayangan sila, or they could have taken that opportunity to have that appreciation even early in school. Um, Another comment is that physics is difficult because it's so abstract and it's intimidating for people who don't necessarily, love math or numbers and equations like maybe some of us did as young students. Maybe also not all, right? So and there's this recognition that numbers and foreign variables can actually easily scare students away. Our letters, symbols, and Greek alphabets that are very actually foreign need to be more gently introduced um, because otherwise it will scare, or it can scare or turn off learners. Um, Again, I don't think this would come as a surprise to us, but this just validates this notion. On the other hand, it's also um, it was also good that many commenters um, pointed to very memorable positive experiences. So, and these are some of them. Um, my physics teacher used a working model rocket. Uh, and then the second memory is that I was asked to push a chair vertically while the instructor pushed it horizontally. And it was my first physics lesson on vector forces. And even without drawing anything on the blackboard, I got the concept and I never forgot. So here we can see how physics lessons can actually make a lifelong impact to learners. Here are more examples. Um, Again, relating to examples that really connected and really stayed with the person. Water from a hose, um, a wind being channeled inside a house during a storm, for Bernoulli's equation, and then this general comment that it's really the demonstrations that the teachers did or that the students did themselves that stays even long after the class. And so this struck me, and putting it together, it's related to this concept, this um, mantra for teaching that's been shared with me called "Start with the World." This flips the traditional sequence of teaching, where you start with a lesson, with a lecture, and maybe do an experiment to demonstrate the lesson, ask the students to reflect, and then only finally get the students to apply it through a project. And so this sequence actually ends with the world. No? Um, but physics is actually all around us, maybe abstract, but it describes the real world. So it can actually be connected to the world of the learner from the start. And one key concept here that was also introduced to me recently is this concept of using realia. So these are essentially just real world objects that facilitate learning and interaction. And, and there are many levels of realia. You have the actual object, um, and in that example, we have the chair, the actual chair in front of you that you can touch, that you can push, that experiences the force that you're studying in physics. If you don't have the actual object itself, it can be a replica of the object or scale model. The next level would be a video, and then a photograph. And then the lowest levels are drawings, which is actually what we do a lot in physics, right? We draw simple figures. And then finally, you can have a written description. But the point here is that we should not take for granted that the higher the level, the higher the engagement. So even as simple as introducing a real physical object or scale model or video or photograph of something before putting it uh, as a simplified diagram can actually will actually provoke the learners and start the learning process very naturally. Um, so the core idea behind Science's Knowledge Channel program, which I'm involved in as host and as co-writer, is centered on this, on using real real objects, simple objects, to do fun and easy experiments to demonstrate science concepts. So here, I'm just showing some examples. For static electricity, you just need the aluminum can, right? The pipe and the towel. You rub it, the pipe with the towel, and you can actually see the can move even without touching it. So classic experiment, but it's really different if you just describe it versus if you actually do it yourself, or if you can show a video of it and encourage the students to do it themselves, maybe at home in this case. Uh, just going through this quickly, we have an example of refraction, and then finally uh, this demonstration of surface tension where you um, have a paper clip floating on top of the water, and then you place just a smidge of dishwashing liquid, and guess what will happen. And it really provides that aha moment, and starts the process of curiosity of why that happened. And that's when you introduce the scientific concept. So there are many of these videos, and we're uploading them new episodes weekly on the Knowledge Channel's Facebook and YouTube pages. So that's the first thing I wanted to share, the idea of starting with the world and using as much as possible real world objects when we teach and introduce physics concepts. The second one is this, again, a mantra from progressive learning, is to create love for the subject. So I pose the question, what if this was our primary goal as teachers? No? Not to drill the students with new knowledge or to how to solve problems, but really to create love for the subject that we love. Um, some observations, if we have this very sole focus on problem solving, it actually leads to feelings of failure and inadequacy. So very negative emotions for students who are not adept at this very particular set of technical skills. So it's an invitation to rethink assessment. So there's a recognition of not just mastery, but an appreciation and understanding of the concepts and even narrating and explaining how they understood them. Further questions would be, um, with the way we teach the subject, how many would-be scientists have we actually turned away from the field, no? Because of these negative emotions, and related to that, how many future professionals, and citizens have we made averse to science even without meaning to? Again, because of these negative uh, emotions that stay with them through their lives. Um, So in my own way, I'm spreading the love for physics through these video explainers on YouTube, where I answer frequently asked questions about science in Filipino, in the vernacular. So I've chosen very popular questions that really come from young people that I've gotten over the years about time travel, aliens, parallel universes, and these are questions that I also had myself. Um, and I also take this opportunity to introduce concepts in quantum mechanics, the many worlds, general relativity, gravitational time dilation, in this case, and electromagnetic spectrum. No? Bakit tayo nakakita ng iba't ibang kulay? So sharing here just some examples. So in this time dilation video, the question actually came from a comment, someone who commented on the channel, and the question was, how does time dilation affect biological aging? And so here I introduced the concept of time dilation, gravitational time dilation, and used Baguio versus Metro Manila as an example. And so this commenter also responded to the video saying that she's now more interested to dig deeper about general relativity. So for me, this is achieving the objective, that is just um, 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 cultivating the love for the subject uh, in these young aspiring scientists. Um, And this is my latest video, and I'll just share so far my best comment so far is this person post his anime for this, and it was worth it. So I hope you could also check these out and share it with your students and young people who are, interested in, curious about the world. And of course, physics is part of how we um, understand the world better. Um, so I'll just leave you with this. Again, people who shared on my Facebook about their lifelong love for physics was sparked by their experiences in school, in high school in particular. And so when they really enjoyed physics, they ended up, pursuing it, and that awe and wonder from these experiences stays with the person really throughout their lives. And this final comment is actually from an ophthalmologist. So he absolutely loved physics. Their teacher really sparked that joy and appreciation in him. And now, as an ophthalmologist, so he didn't pursue physics per se, but now he's a professional, ophthalmologist, and also he's a teacher. So he teaches light and optical physics to residents of ophthalmology. Um, so I leave us with this reminder of how far-ranging the impact um, of our teaching goes, and if we, number one, try to start more with the world and introduce physics in a way that relates to the world of our learners, and number two, we approach our teaching of the subject as with the goal of creating love for physics in all of our students, I think it can go a long way to making physics less intimidating and having more Filipinos appreciate and love science as they grow up, and maybe even encourage more young Filipinos to go into physics and join us, join our community. So I'll just want to acknowledge everyone who shared in my Facebook posts and my YouTube videos, and of course the Sciences team at Knowledge Channel, and special mention to Mikey Cuento, who's a high school teacher in a progressive school that shared these very helpful ideas with me. Thank you very much.
Hello, I'm Nat Hermosa. In this short, intimate talk, I will reveal my group's not so secret process of creating ideas. While this process may be personal and unique to our group, I hope to accomplish two things. First is to give young researchers a sort of template as they try to determine their own creative processes. As budding scientists, we usually have difficulty knowing where to start. And second, I want the audience to reflect and be conscious of their own methods of creation, to be aware of what works for them. Scientists are expected to be creatives. The process of creating ideas eases the burden of making them. I'll start with this figure, the Penrose stair. In the account of Manjit Kumar, it was said that Roger Penrose conjured this impossible figure with his father, Lionel, as Roger was attending a conference in Amsterdam. He got inspired by the exhibit of M.C. Escher happening just across where his conference is at. Roger and his father, Lionel, produced a psychology paper about it. When Escher got hold of the paper, it inspires him to produce two masterpieces, Waterfall and Ascending and Descending. Here in Ascending and Descending, two lines of identically dressed men appear on the staircase, one line ascending while the other descends. By Escher being inspired by the work of the Penroses, it completes a cyclical flow of creativity. But Penrose was not the first one to design an impossible figure. Oscar Rutterswald first created an impossible triangle in 1934. According to Thomas Gate, the triangle abruptly becomes a dizzying experience as its bottom link plays havoc with the brain's intuitive knowledge of physical laws. These impossible figures and how it wreaks havoc on our intuition brings me to the question of creativity. Creativity, according to Edward Wilson, is the innate quest for originality, the driving force in humanity's distinctive love of novelty. We follow creativity inward, toward the greatest depth of our shared minds, and outward, as scientists, to imagine reality across the universe. Goals achieved lead to further goals, and as we saw from the flow of creativity from Penrose and Escher, the quest never ends. But where do we start? We look at what two Nobel Prize winners said, Albert Einstein for physics and Bertrand Russell for literature. They said that knowledge must be digested and eventually emerge in the form of fresh, new combinations and relationships. To millennials, this would mean creativity is just connecting things, as Steve Jobs would say. But I'd like to use the framework of James Webb Young. To him, the habit of mind, which leads to a search for relationships between facts, becomes of the highest importance in the production of ideas. I will analyze my own creative process based on James Webb Young's 5 ways of producing ideas. But why is it important to us to know where we get ideas? Scientists are creatives. Being creative is not only expected from us, but should be natural to us as well. As human beings, we have downtimes or phases in which we tend to have difficulty coming up with innovative ideas.
Therefore, we need to be familiar with our own creative processes. Knowing the process of creating ideas eases the burden of creating ideas. We always say that imagination fuels science, but as scientists in training, imagination is an abstract concept, and we grapple on how to make it into concrete and tangible processes. Is there a process of producing ideas? As I said, this talk is about James Webb Young's technique of producing ideas via some of my own research work that came out that are loosely based on this process.
The first step is the most boring but perhaps the most important step among the process. How can you connect things and produce something from these things without first gathering them? Inspiration does not arrive as fast as we want it. I usually tell my students that for us to move forward, we must read a lot. Actually, gathering materials take time. You cannot gather faster than normal because part of these materials are our own experiences. One cannot hasten all these experiences. You also cannot read as many papers or books as you want. There is just not enough time. So how do you gather information with ease? Well, be fascinated with a lot of things. For example, I am interested in evolution and coevolution, history of thought and science, epistemology, even etymology, beyond my usual interest in optics. And what do you do with this information? You put a number of information in a browser so that you can quickly examine for relevance, which may or may not lead to a closer examination of this information. Browsing is a kind of orientating strategy. It is supposed to identify something of relevance. What do you do next? This material. That's step two. You digest them. Be that curious octopus. Connect things. You orient the information you have in your browser to connect in your puzzle. To do this is to use metaphor. The moon is an apple. Initially, by choosing that metaphor, we know that the apple and the moon are similar in a very important way. When we realize that they are similar in that they obey the same laws of motion, its scientific connection is revealed. However, it's still qualitative. Therefore, the next step, according to David Bohm, is to transpose the unfolded metaphor in a mathematical language, which renders the similarities and differences more explicit. From there on, calculations are used to compare theory with experiment and explain in detail why all objects fall and yet some, like the moon, never reach the surface of the Earth. Let me give you an example with one of our research from 2016. It got a lot of attention both here and abroad. To me, the connection to produce this idea is easy. Back in 2015, there was a science paper from a group in Glasgow that says by spatially structuring photon, the information carried by this photon will travel slower. What strikes me is this figure, this focusing that actually adds extra length traveled by the photon. By focusing, the direction of momentum gets skewed. So even though the speed of light is the same, the distance it traveled is longer, hence a longer time interval for the information to arrive. Which reminded me of the paper we published last 2013. When we got our papers reviewed, the reviewers asked us to reconcile with the results of another paper just published a few weeks after our submission. In the science paper, the treatment is purely geometrical and relies on the path of light, contrary to our model that is based on the phase of it. So I did the mathematics. I got the idea from a 1992 paper on orbital angular momentum. In their work, they have described a pointing vector for light beyond the Gaussian beam. I took the direction of that pointing vector as a direction of displacement for the light reflected by the particle and used the Doppler effect equation. It was, I guess, for me a straightforward connection. In this case, the metaphor is that the pointing vector is a direction of a displacement. I derived the equation and come up with the same relation as that of Lavery. It was geometrical for Lavery and it was to us based on the shape of the beam, which leads me to our original problem. If the beam is 1 meter long, If a lens that changes the direction of the beam by focusing changes the direction of the pointing vector changes the group velocity of a beam, then a twisted face, which has a corresponding pointing vector, will affect the group velocity of the beam. That's the story behind the paper of Mr. Pereza. The third step is unconscious processing. When I was younger and tried to solve problems in physics, I would walk inside the campus and just forget about the problem. Maybe something will come up, or maybe nothing will come up. When I got a little older, I mindlessly shop in a supermarket or hardware stores, going between all lanes just to detach myself from the problem of maybe give me new insights on how to solve it. Nowadays, my unconscious processing happens when I read books, I drive, or go to ABC. It is important to rest and let the mind wander and devote time to what stimulates your imagination and emotions. To my students, sometimes um, they dance. Give you an aha moment during unconscious processing. This video here is a helioconical beam as it reconstructs itself. Prompted me to investigate this property is its conical shape. Vessel beams have conical face and itself reconstruct. It was easy to see the connection that helicoconical beam with its conical face can also self-reconstruct. I did a simulation, went to Austria. I abandoned this topic because the only thing I have was a simulation during that. While having a KitKat break, I just had an aha moment. I remember that what prompted me to investigate this property is its conical shape. Vessel beams have conical face and itself reconstruct. Since I know better now, I've reconstructed the helicoconical beam as a sum of vessel beams of different radii. And I was able to derive the limit based on the beam parameter, a solution to a 6-year problem. The fifth step is idea meets reality. We need to submit to criticism. Criticism can be internal and external. Internal, you have experimentation, and you ask your group mates uh, what do they think about your idea. External is when you submit your manuscript to a journal and the criticism is in the form of review. Conference criticism is more real time. Usually, people ask questions at the talk or approach you after the talk. I got the page from Isaac Asimov's playbook. In my group, we have Crazy Idea Monday, or now we have Crazy Idea Friday. The idea is this. For best purposes, there should be a feeling of informality, joviality, the use of first names, joking, relaxed, kidding are, I think, the essence, not in themselves, but because they encourage a willingness to be involved in the folly of creativeness. For this purpose, I think a meeting in someone's home or over a dinner table at some restaurant is perhaps more useful than one in a conference room. In my group, what we do is we eat. If thoroughly relaxed, free of responsibility, discussing something of interest and being by nature unconventional, the participants themselves will create devices to stimulate discussion. Has it been successful for us? The first crazy idea that came into reality is the group velocity dispersion. The latest, perhaps, is the one that will be presented by Miguel in this year's SPP. We also see that experimentation is a form of self criticism. In this paper by Renish, we saw that graphene is a thin film with measurable thickness. But it's not always the case. There are 3 models in which she can describe reflection of a light from a graphene, a single layer graphene. Actually, one of these models I prefer much, but as Renish did the experiment, we saw that I was wrong. To quote Feynman, we say the test of all knowledge is experiment. Experiment is the sole judge of scientific truth. In this case, we need to judge between the 3 models. I did become critical of my own self.
In summary, one of the main jobs of a scientist is to be creative. Hence, it is important for us to recognize and understand our own creative process. Connecting the dots is a sure way to produce new ideas. And if you are in a rut, you can follow James Webb Young's 5-step process in creating ideas. We gather information, we digest the material, we do unconscious processing, we wait for the aha moment, and we submit to criticism. But one thing is lacking here, and that is to have courage. When we create new ideas, be it as crazy as possible or as plausible as it is crazy, it takes a leap of faith, and you need courage. Thank you very much.
The Instrumentation Physics Laboratory of the NIP in UP Diliman. As an overview, collective decision-making involves multiple strategies applied in different scenarios. The local acceptance model quantifies these interactions of agents among small neighborhoods. We apply our model on various Watts-Strogatz networks. So collective decision-making is the complex process by which a group reaches a decision. Our decision strategies often include the majority rule, minority game, random choice, and many others. We have social networks, such as ordered, small world, and random, to depict the relationships among agents. An agreement can be among a population, within a smaller neighborhood, or between any two pairs of agents. So the local acceptance model incorporates over 25 decision-making strategies in various contexts. We have alpha as the probability that an agent copies the neighborhood majority, so the majority state among its small group of friends. Alpha equals 1 depicts the majority rule. Alpha equals 0, the minority game. 0.5 corresponds to random choice, and you have a combination of other parameters and values. So here we have the famous Watts-Strogatz networks, which depict relationships among agents. For the regular, you are only connected and interacting with those people around you or the agents around you. For random, you can be connected to anyone along or around the population, and the small world is a combination of those two types. So here are parameters for our model. So we have the network disorder for the three common Watts-Strogatz networks. A population of 1,000 is sufficient to recreate a big population. We have a common number of neighbors, 7. We have 2 initial states first and several runs and iterations. And especially we have memory wherein an agent also interacts with itself, meaning it also reinforces its own state when it considers how it will vote or what will be its state in the next iteration. And we used Python for our program. So here are our results and discussion. So basically, we have for the first column, global agreement, agreement within a population, as in we have voting for a nation. For the second row, or second column rather, we have neighborhood agreement, agreement within your small group of friends. And for the third column, we have pairwise agreement, when we list the agreement between any two agents that are already connected. So first, we have global agreement. There's a significant majority if we have maximum disorder. That means the more interactions you have with anyone in the population, there's a bigger chance for a global agreement. So remember, when we have disorder, this is the case of having an internet which is connected worldwide. And we see a threshold at alpha at around 60%. So there is a threshold when we have from undecided 50-50, we have a significant majority after that threshold. And for pairwise agreement, again, the agreement between any two agents, it is proportional with local acceptance. And this is logical because remember, local acceptance is the agreement within your small circle of friends. So the agreement between any two pairs of agents would be proportional to that alpha. Meanwhile, for neighborhood agreement,
agreement within that small circle of friends. So it is a combination of population and pairwise agreement. So like before, we have a threshold similar to the population agreement, and we also have a proportionality beyond that threshold. So for our conclusions, we applied the local acceptance model for various Watts-Strogatz networks. Multi-scale consensus, agreement along different scales, is observed for agents with high local acceptance, so high agreement within their small circle of friends, and within disordered networks, when we allow communication along a large amount of the population. The study can be extended by varying the parameters, especially the population and neighborhood sizes, and by introducing heterogeneity in our agents. So having agents with various properties, such as memory and local acceptance values. So that is all for my presentation. Thank you for your time.
Welcome to this presentation entitled Synchronization of Individual Heading Deviations in Finite Flux of Self-Propelled VIXEC Particles. I'm Marjibel Nengal from the Department of Physics of the Mindanao State University, Marawi City. This is the outline of my presentation. And let us begin with the question, what is active matter? This 2016 paper entitled Active Particles in Complex and Crowded Environments provides a comprehensive review of active matter research through the years. Based on this paper, active matter is composed of self-driven or self-propelled units, also known as active particles, each capable of utilizing stored energy or free energy from the environment and converting that into persistent, directed motion. In 1995, the group of VIXEC first proposed a simple model for the collective motion of active particles. Over 2 decades later, active matter research has flourished into a highly multidisciplinary field encompassing field and laboratory experiments, mathematical methods and models, and computer simulations. Nevertheless, most active matter simulations to date have focused primarily on the effect of noise and density parameters on the evolution of particle trajectories and headings, as well as the characteristics of the order-disorder transition. In this present study, we revisit the VIXEC model for collective motion and investigate the degree of phase and amplitude synchronization of individual heading deviations from the flux global direction. That is, by employing the Kuramoto order parameter and the mutual information metric as phase and amplitude synchronization quantifiers, respectively. The standard VIXEC model is quite simple. At each time step, a given particle driven with a constant absolute velocity assumes the average direction of motion of the particles in its neighborhood of radius r, with some random perturbation added. That is, the position r sub I and the heading theta sub I of particle I are updated according to these two equations, where v sub I bar is the neighborhood average velocity of particle I, and theta sub I bar is the corresponding average heading. The random perturbation, delta theta, is a temperature-like variable chosen with a uniform probability from this interval, and with intensity eta in the range 0 to 2 pi. For the SVM ensemble, the usual order parameter phi is the magnitude of the average normalized velocity. And phi is equal to 1 if and only if all the particles in the system are moving in the same direction. This video shows a sample realization of a VIXEC system with 95 particles and noise intensity equal to 0.1. We can see in this video that for a VIXEC system with high particle density and low noise, the initially disordered system exhibits collective motion over time. In this paper, the group of Atanasi and Cavagna defined the directional correlation between the direction of motion of an individual bird eye and the global direction of motion of the flock as shown. Now, as emphasized by Cavagna et al. In another paper, characterizing the departure of individual behavior from the group average is important, particularly when probing a system's collective response to external perturbations. Hence, in this present study, we want to ask, what are the effects of varying noise intensities on the synchronization of phases and amplitudes of individual heading deviations in finite Vexec flux. To quantify amplitude synchronization, we make use of the mutual information metric. The mutual information I of two time series, CA and CB, evaluates how much information CB gives about CA that is not present in CA alone, and vice versa. If the time series are independent of each other, I is equal to 0. If the time series are in any way correlated with each other, I is greater than 0. To quantify phase synchronization, we make use of the Koromoto order parameter ρ sub k. This is a measure of the synchronization of the end signals during the entire time spanned by the signals. It measures correlations of the phases rather than of the amplitudes of the time series data. To facilitate comparison among the three parameters, phi, ρ sub k, and I, we resort to a time-resolved study. That is, for each Vexec simulation run, we partition the entire data file into non-overlapping 5,000 point epochs, and then compute phi, ρ sub k, and I for each epoch. For n is equal to 100, I is averaged over 4,950 unique neighbor pairs. Here are some representative plots of the time evolution of phi, ρ sub k, and I for eta is equal to 0.1, 0.3, and 0.9. Results show that for the range of noise conditions examined, the trends in ρ sub k values is positively correlated to the trends in phi values. For instance, in figure A, both phi and ρ sub k saturate to their maximum value of 1 within the first 10,000 time steps. This suggests that the system's transition from an initially disordered state to a state with ordered directional velocities is accompanied by the collective phase synchronization of the members' individual heading deviations. If we look at the time-resolved behavior of I, we see that the average mutual information between pairs of individual heading deviations exhibit substantial variation over the course of a given simulation run. This suggests that even when the Vexec system has already transitioned into a state with ordered directional velocities, the degree of amplitude synchronization of individual heading deviations may still exhibit significant variations over time. By plotting the time average ρ sub k values against the associated phi values, we find that the two order parameters phi and ρ sub k essentially track each other. The equation of the best fit line, shown in figure D, has an R-squared value of 0.978, indicating a high degree of positive linear relationship between ρ sub k and phi. Figures E and F, on the other hand, shows that the average mutual information of individual heading deviations diverge as noise tends to 0. In summary, through numerical simulations of Vexec systems at fixed particle speed and density but varying noise intensities, we find that the synchronization of phases and amplitudes of individual heading deviations are independent of each other. For the simulation parameters considered in this study, the mutual information tend to diverge as eta approaches 0, while the Koromoto order parameter saturates to 1 at very low eta. It must be noted that in this time-resolved study, the epoch length is chosen solely for ease of visualization and comparison among the time-averaged phi, ρ sub k, and I values. In future works, it would be interesting to explore how the collective phase and amplitude synchronization behavior will change under different epoch lengths, durations of simulations, flux sizes, particle speeds, and other parameter changes. That is all, and thank you for listening.
Good day, everyone. This is a presentation of our work on Verhulst and bifurcation analysis of a neuronal network on an outer totalistic toroidal cellular automata with Dr. Janro Bantang and myself. I am Rainer Sander Ramos, and we are from the National Institute of Physics, University of the Philippines, Diliman. In this study, we explored the dynamics of a population of interconnected neurons on a cellular automata model. We analyzed the cobweb diagrams and found out that non-zero steady state is an emergent property. Also, we observed bifurcation where period doubling happens at negative slope activation function. This implies a possible way of modeling epileptic neurons. Finally, we propose our classification of neuronal CA as follows: zero steady state, non-zero steady state, and periodic state. This will be the outline of our discussion. First, we will tackle about the activation function. The figure on the top right shows the nonlinear response function of a typical Hodgkin-Huxley neuron. Here, Alan Hodgkin and Andrew Huxley formulated a system of coupled nonlinear differential equations to describe how action potentials are integrated in the neuron. They compared their results with experimental data on giant squid axon and obtained the firing frequency while increasing the input current injected into the neuron. As you notice, there are regions in which an input current is injected but the neuron did not fire. Also, there is some maximum firing frequency that the neuron can attain, and the response is almost linear with a positive slope. These characteristics are also observed on the input-output profile of other neuronal models, but with different current values depending on the system of differential equations used. So, we transform these response functions into a normalized activation function shown in the left figure. The dashed line is the y is equal to x line, which will be important for our cobweb analysis. We also incorporated the characteristic thresholds given by a sub 0, a sub 1, and a sub 2. This linear function as described by equation 1 will serve as the rule for our cellular automata. In our cellular automata, we arrange 10,000 neurons in a 100 by 100 toroidal lattice. For a toroidal lattice, as shown in the left figure, we wrap around the edges so that the cell X in the corner will be connected to the blue shaded cells. We combine this with an outer totalistic Moore neighborhood so that the cell of focus itself is included as part of the neighborhood. At time t equals 0, each neuron has a random activity taken from uniform distribution from 0 to 1. The rules for each neuron is to take the average of the neighbors, including the activity of the neuron itself, and then map the obtained value to the output using the activation function. We found out that a duration of 100 time steps is enough to achieve steady state. We simulated all possible combinations of the thresholds a sub 0, a sub 1, and a sub 2. That results to a positive slope activation function. We found 4 different types of spiking activity as shown by the figures on the top row. Here, the lighter the color of the cell, the higher the spiking activity is. The corresponding trajectories in state space of each of these figures are shown in the bottom row. Here, we plot the previous average state of the patch versus the next average state. The blue dot indicates the initial state and the red dot indicates the steady state. Notice that the first two CA on the left have 0 steady state, with the second one having longer spiking duration. The last two CA on the other hand have non-zero steady state, with the second one having exploding patterns at the first few time steps. We can compare the patch trajectory with the individual trajectories of each neuron by doing a cobweb analysis. Here's how we construct a cobweb diagram. Consider the sample activation function in figure 4, where the dashed line again indicates the y is equal to x line. Let's say that the neuron has an initial state indicated by the blue star. First, draw a vertical line from the initial state to the activation function. From here, draw a horizontal line to the y is equal to x dashed line. Continuously, draw another vertical line to the function. We repeat the previous steps for more iterations until we observe a steady state indicated by the green triangle. In this specific case, 5 iterations is enough to observe a 0 steady state. We do this for each of the types of CAs we have earlier and compare with their respective state space trajectories. The cobweb diagrams in figure 5 shows 3 different cases for which the neuron could be initialized given the activation function. As we can see, all these neurons ended up into a 0 steady state, as expected with the overall behavior shown by the state space trajectory. In figure 6, there is one possible case that the neuron ends up at a non-zero steady state. This is when the neuron is initialized at the intersection point of the activation function. This is why the spiking activity of this type of CA takes a longer duration to reach zero steady state. We call these types of CA class 0, which can model inhibitory neurons. Here, we have the latter two CA types. Notice that in the cobweb diagrams, all neurons end up in a zero steady state, but the overall trajectory is non-zero. This only happens when the intersection point of the function with the dashed line is at the origin. Activation functions with smaller difference between A0 and A sub 1 tend to have exploding patterns. Excitatory neurons belong to class 1 in this scheme. Now, we look at some representative bifurcation diagrams. This time we include the negative slope activation function on our analysis. Each plot in figure 9 shows the steady state values versus increasing A sub 2. The inset shows the activation function for that parameter set given that A sub 2 is equal to 1. We found out that period doubling is most noticeable for negative slope activation function. However, only period 2 bifurcation were observed. Periodic steady state is a characteristic of an epileptic neuron. For completeness, we present the dynamics of the epileptic neurons. The first 4 plots on the top row are the cobweb diagrams, where in 3 out of 4 possible initial cases, the neuron will oscillate along the red square trajectory. The two-state oscillation is also noticeable on the state space trajectory shown on the bottom right, where the neuronal patch traverses back and forth along the blue line. The spatiotemporal activity of epileptic neurons is shown in the top right figure. In summary, we analyzed the cobweb diagrams, bifurcation diagrams, and state space trajectories of our neuronal CA model. We conclude that there are 3 classes possible for our CA model. We have the class 0, which models the inhibitory neurons, the class 1, which includes the excitatory neurons, and class 2, which describes epileptic neurons. Thank you for listening and have a COVID-free day.
Good morning, I am Lou Joseph Tan and I will be presenting our paper entitled A Post-Based Action Recognition Machine Learning Framework for Basketball Analytics. To start, I will introduce the 2 popular tasks in the field of computer vision, which are post-estimation and action recognition. The former deals with the interpretation of movements on a physical level by reconstruction of motion. So in the sense of the human pose, this is essentially the localization of human joints from images or videos. And then the latter deals with the understanding of these movements over time on a higher semantic level. But despite the differences between these two, there is actually a significant information overlap in that an action may be a subset of all physically possible poses, and a pose may be a strong indicator of a particular action. However, these two are not trivial tasks, and so challenges are inherent to both, and majority of the researches in these 2 topics are dealt with separately and rarely together. So in this paper, we will be presenting 2 machine learning frameworks for a post-based action recognition system. We'll basically be utilizing body poses to infer actions from a sequence of frames. So in the context of basketball analytics, these may lead to at least the following insights. First would be the analysis of the kinetic chain or the body coordination of players through pose estimation, and a more comprehensive and deeper player tracking through action recognition. So in the following slides, I'll be discussing the frameworks used for both, mainly discuss the network architecture, the training details, including the data preprocessing, and then the results, including the evaluation on unseen data. So for post estimation, we use stacked hourglass networks by Alejandro Newell et al., which effectively alleviates the following problems. It handles the problem of generalizability well, meaning that it performs better in the presence of occlusions, and then the process of stacking allows for the refinement of post predictions. Note that each block in this architecture is a residual block containing 3 convolutions and then a skip connection, and that the goal of this network is to capture information at every scale. So what it first does is it processes features to a very low resolution, And at each pooling layer of these blocks, you branch off and then perform convolutions on the pre-pooled resolutions. And finally, at the lowest resolution, you upsample and then combine features from these branching connections via element-wise addition, like so. And so what these skip connections do is that it aims to preserve spatial information across scales, so from the highest to the lowest resolutions. At the end of the network, you add two more convolutions for the network predictions, and then you stack these together end to end and apply loss to the intermediate heat maps for the refinement of the network predictions via intermediate supervision. For this, we'll be using the MPII human post dataset containing annotations for 16 body joints and the center and scale annotations, which we'll be using for data preprocessing, since we only aim to perform single person post estimation and the images contain multiple people. So this is our data preprocessing. You center around a central person, and then you apply a Gaussian function to produce the ground truth heat maps. Here are our hyperparameters, and the evaluation was done using the percentage of correct key points, where a detected joint is considered correct if the distance between the prediction and the ground truth falls within a certain threshold. And here are the aggregated results. Here are also the PCK curves at different thresholds. And if you'll notice, we obtained the lowest accuracy score for the wrist and the ankle, not to mention the knee. And accordingly, we achieved the lowest curves for the wrist and the ankle. Rightfully so, this is where most of the occlusions occur in the appendages of the body, as compared to the more axial part, which contains the head, the thorax, or the pelvis. Okay. Here are some sample predictions on the MPI dataset, and here is a sample prediction on jump shot clips of basketball players. Moving on, we used 1D convolutional neural networks for action recognition, where we used our proposed distance spreads as input to the network, and then perform a series of convolutions, and the final output, which would be the action classes. So distance spreads is a dimensionality reduction technique that seeks to reduce the time sequence of moving body joints into a more compact spatiotemporal representation, which cuts away the computational costs of having to train on multiple image frames along a temporal dimension into just a 2D input. So the process begins with a series of estimated poses. You take the distance of the joints to a designated body center, which we define to be the thorax, a midpoint between the thorax and the pelvis. And then you stack them as row vectors like this. And for this, we will be using the SpaceJam dataset containing 1 second clips of 10 action classes. However, we'll only be using a subset of 3 classes because we still had to manually annotate the ground truth for this dataset. So we were able to, all in all, we were able to create 480 distance spreads for training and 120 distance spreads for testing. And here are our hyperparameters for action recognition. And then here are our results. Here's the confusion matrix for 120 distance spreads with an overall accuracy of 96%. And I think it's worth noting the limitations of this system. Of course, as the title suggests, the network is purely a post-based action recognition system. So it won't be able to pick up visual cues from images or videos, meaning that it won't understand if a player is holding a ball or moving off ball. And also, the distance is variant to the orientation of a player with respect to the camera. So it's a variant feature. To conclude, we presented 2 machine learning frameworks which may be used together for a post-based action recognition system, where we leverage the poses to use in an action recognition. First, we get image frames, pass it to the stacked hourglass networks, get the process, transform it to distance spreads, feed it to the action recognition system, and then you get the air action. So separately, we're able to obtain 79% overall accuracy for 16 body joints and 96% accuracy for the three action classes. For future studies, extending the model to include more classes and utilize more features is advised. Here are my references for these slides, and thank you.
Hello, everyone. Good morning. So I'm JC Paralta, and I'm happy to share to you our work on determining the transportation network efficiency during disaster events. In recent years, no, a major theme of complex system studies is determining how well a particular network configuration could perform under scenarios of, say, diminished performance. So, say, like here in this classic study of Albert Jong and Barabasi, networks in the internet, like the internet and the World Wide Web, were modeled, and they were assessed to be robust to random failures, but sensitive to targeted attacks. Now, with open mapping platforms gaining popularity, much work has also been done on assessing transport networks using the complex systems approach. So here in Xie 2015, they assessed the exposure of Taiwan's roads to, to natural hazards and how it impacts flight systems servicing Taiwan cities. Now, this has been also been done locally. No? So here, say in Valenzuela 2014, they assessed the impact of simulated random damage to the road network of Tacloban City. So what we have studied here in this work is the road and sea route network connecting the major islands of Visayas region. So we gathered this data mainly from OpenStreetMap, and this is what it looks like when it's mapped. So we've got 408 town centers with 16 airports and 70 seaports, and then the road network is as shown now. Now we want to use this model to simulate a relief distribution operation. So this is what it looks like. So starting from the regional DSWD hubs as shown, which serves a particular region, and in particular uh, Region 7, Cebu region has two. No, so if we start from those and then go to the town centers, if we plot the travel time, no, from the town center to its nearest food hub per region, this is what the chloropleth map would look like. So towns with near big cities like Iloilo, Cebu, Dumaguete, I think, and Tacloban are reachable within 1 to 2 hours, while far-flung areas of northern Samar and eastern Samar, no, can take up to 10 hours to be reached. But these travel times assume a fully functional network. No. Now, what we want to do is to simulate damage by removing nodes within a certain area and up to a particular threshold. So this map shows a sample of that scenario. No? So it's for a 0.05 damage to the transport network along the damage radius of Typhoon Haiyan. So we ran this over a range of damages, and we did that for 100 trials each. How then would the travel time distribution from food hub to town center change given this damage? So as we have done in the Visayas network, we assigned random food hubs and town centers to three synthetic networks for comparison. No? So we've used a square lattice, a Barabasi Albert network, and a small world network. And then we compared the results of these simpler relief distribution models to that of Visayas. So here are the results when we plot the travel time from the food hub versus the number of town centers reached within that particular time. No? So we note here that the travel time is scaled by a factor T naught, where T naught is the time where the simulation reaches 80% of the town centers on the baseline scenario. So we see that for Visayas, a small damage as small as 0.50% already has an impact, and a damage of 2%, for example, will reduce the service town centers down to 80%. We contrast this with the lattice network, which is highly robust and has substantial difference only after around 35 to 40% damage. On the other hand, BA, Barabasi Albert, is less robust than Lattice but more robust than Visayas. The damage we see being substantial after around 10%, 15%. And then lastly, we look at the small network now. When we look at this, we notice that like Visayas, it also has a sensitive threshold, no, and it shows significant substantial difference even at less than 1% damage. So now we quantify that decrease in performance using the relief delivery efficiency metric over all town centers, which is given by this formula. And then we know that from the configuration of the synthetic networks, it changes given a particular time seed. So to cover for that variability, we made an ensemble run of 100 instances of each of the synthetic networks compared to the single Visayas simulation. So now if we look at the efficiency curves for each net of the networks, we see that the small world, the green one, is indeed the closest one to Visayas. And that's most interesting to us because this resemblance could be a good starting point to uncover more properties of the Visayas network. We also believe that our results highlight the vulnerability of the transport network and that's push for strategic prepositioning of relief goods before the disaster and maybe air deliveries not relying on the on-ground transportation infrastructure after the disaster. And then lastly, having built this model, we also see it as a strategy testing tool for our decision makers to mitigate impact of say transport disruptions rather, not only due to natural hazards like earthquakes, typhoons, but also government enforced ones like local quarantines and lockdowns, blockades, etc. Thanks everyone.